Hi everyone, welcome back. This is going to be a video about the characteristic equation for linear algebra, and this is going to continue the discussion we had last time about eigenvalues, eigenvectors, and eigenspaces, and we talked a little bit about how to find them, and this section is going to sort of formalize that a little bit more, and we're going to do a really long 3 by 3 example, and I think we'll also have time to do another one that's maybe a 2 by 2 example. But right now we're focused on finding eigenvalues, finding eigenvectors, and how do we do that? So let's get into this. Okay, so in this section we need to see what is the characteristic equation and what does it have to do with eigenvalues. And believe it or not, the characteristic equation is something that we've already seen. We just didn't really give it a name. So in the previous video, we actually looked at the characteristic equation. So let's maybe recall something from the previous video. So example from previous lesson. We had a 2 by 2 example. We were given a equals 1, -2, 1, 4. And our question right now is, what are the eigenvalues? And you could refer back to that previous lesson if you need to remember what the definition of eigenvalue is. Now, if I recall, I think that this was an example where I gave us one of the eigenvalues and one of the eigenvectors, maybe. But then we went through a process to try to find if there were any more. And in the end, we did find that this had 2 eigenvalues, which means it has basically 2 eigenspaces. In general, to be an eigenvalue, we want ax equals lambda x. That would make lambda an eigenvalue. To make lambda an eigenvalue, right? And then x would be an eigenvector. Well, what did we do? We did this this equation. I mean, this is an equation, right? Left-hand side equals right-hand side. We subtracted to make it look like this. And then we did kind of an interesting type of grouping where we said that this actually could be written as A minus lambda I, where I is the identity matrix. All right, we did this last time, and A minus lambda I is something that we can figure out because we know what A is, and we want to find out what lambda is, but we know what I looks like. So let's just focus in on this part, and let's say A minus lambda I is a matrix. This whole equation right here looks like a homogeneous equation because it's a matrix times a vector equals the 0 vector. Right? So this is a homogeneous equation. The matrix is not A anymore. The matrix is A minus lambda I, but it's still a homogeneous equation. And there are non-trivial solutions if and only if its determinant is, what do you think? Do you think I need to say 0 or non-zero? It's one of those, right? 0. If A minus lambda I has a determinant equal to 0, then this homogeneous equation has non-trivial solutions. Now remember, the definition of eigenvalue, let's take a step back. Definition of eigenvalue said that this equation right here, ax equals lambda x, it must have non-trivial solutions. We know it has the trivial solution, x equals 0. But that doesn't count. We need to know if there are non-trivial solutions to this. Now, in the previous video, the previous lesson, when we had this, we found this determinant, and we set it equal to 0, and we solved. We did, like, you know, the determinant was, I have in my notes that we did something like this. We factored, and we found lambda equals 2 and lambda equals 3. I'm going to put this whole thing in parentheses here. Just kind of, that's how it applied to that problem. So you take the determinant of a minus lambda I, and you set it equal to 0, and solve. And when you get two eigenvalues like this, you could say lambda equals 2, lambda equals 3, or if you prefer, you could call this like lambda 1 and lambda 2. We might do that sometimes. Now I'm ready to tell you some definitions. This was a quick recap of how we found eigenvalues. There's a little more work if you also want to find eigenvectors. Okay, definitions. The determinant of a minus lambda I equals 0 is called the characteristic equation of A. The characteristic equation of A. And it is an equation that helps us find eigenvalues. All right, key idea is the characteristic equation is a determinant equation that helps us find eigenvalues. Let's see. The left-hand side of this equation also has a name. Just the left-hand side by itself is a polynomial with unknown lambda. That's usually what we're trying to solve for, right? But if you just think of the left-hand side, I mean, you could see in this case it would be lambda squared minus 5 lambda plus 6. That's the left-hand side. And it is called the characteristic polynomial of A. So if we have the entire equation, it's the characteristic equation. If we just have the left-hand side, it's called the characteristic polynomial. So this is why I said the characteristic equation is something that we've already seen before. We just didn't really give it that name until now. I'll tell you a key idea is that eigenvalues, lambda, are solutions to the characteristic equation. Once we know eigenvalues, we can determine eigenvectors and describe eigenspaces. What do I mean by describe? Well, let's just talk about this sentence here. I kind of just went over how we find eigenvalues. How do we determine the eigenvectors? Well, we did that last time also. It's basically once you know, let's say an eigenvalue is 2 or an eigenvalue is 3, you go back and put it into this equation and try to find x, right? Like you could put it into this and try to find x, and that's going to help you find an eigenvector. Describing eigenspaces, I use the word describe. What I mean by that is we can find a basis for each eigenspace. The best way to describe an eigenspace is to give a basis. So once you have the basis, you've basically found all of the eigenvectors in that eigenspace. It's probably, the eigenspace is the span of something. So let's do a big example. I'm going to walk us through it, and we'll do the whole thing. We'll find eigenvalues, we'll find eigenvectors. We'll break it down into steps. In fact, this is a big example, so I think I'm going to move this entire page away. So you can pause if you're still copying anything from that. All right, let's make room for a big example. We're going to be given a 3 by 3 matrix, A equals 5, 4, 2, 4, 5, 2, 2, 2, 2. And the problem is going to tell us to find the eigenvalues and bases for the corresponding eigenspaces. I'm going to walk us through this. This actually takes a while. So I'm going to tell you that this problem will be a 3-step process. 3-step process. Step one is going to be, let's find the characteristic polynomial. Before we can use it, we need to find what it is. So the determinant of A minus lambda I. Let's work on finding that. Or another way we could write it is just with the vertical bars, that notation, A minus lambda I with vertical bars around it. And let's write it out. You know what lambda I looks like. So A minus lambda I is going to be 5 minus lambda, 4, 2, 4, 5 minus lambda, 2, 2, 2, 2 minus lambda. So we need to find the determinant of a 3 by 3 matrix. It's not the determinant of A. Be careful about that. It's not the determinant of A. It's the determinant of this. So you know how to find a determinant of a 3 by 3 matrix? It would have been nice if there were some zeros somewhere in this, right? But there's not. So let's just go through the usual process. I'm going to take the first entry and then the determinant of this 2 by 2. This is cofactor expansion across the top row. 2 minus lambda. Then we do minus, right? Remember, we alternate plus, minus, plus. So there's the 4 from the top row times the matrix we would get if we removed the top row and the middle column. So 4, 2, 2, 2 minus lambda. And then plus 2, that's the 2 in the upper right, times this determinant. Okay, we've got a bunch of 2 by 2 determinants in here. We know how to do those. So this is 5 minus lambda times. All right, let's get started with this. This is 5 minus lambda, 2 minus lambda, minus 4. And then we have minus 4. 4, 2 minus lambda, minus 4, plus 2, 8, minus 5 minus lambda times 2. I mean, this is it, right? This is the characteristic polynomial. The unknown is lambda, but we'd like to clean it up a little bit. So what I started doing is let's expand some of the stuff in parentheses, some of the innermost parentheses. Let's deal with those. So the 5 minus lambda, we'll keep that on the outside, but let's like work with what's in here, what's in here, what's in here. So I got, let's see, 10 minus 7 lambda plus lambda squared minus 4. And then minus 4, 8 minus 4 lambda minus 4 plus 2. And then in here, I have 8 minus 10 plus 2 lambda. Let's do another simplifying step, because I definitely see some terms that we can combine. Also, with polynomials, we usually write the highest power first. So let's go lambda squared minus 7 lambda plus 6. And then minus 4, this could be 4 minus 4 lambda. And then this could be plus 2 minus 2 plus 2 lambda. Okay, well, we could expand this now, right? Distribute this. And we could distribute all these things too, the 4 and the 2. So if you do this, you get 5 lambda squared minus 35 lambda plus 30 minus lambda cubed plus 7 lambda squared minus 6 lambda. That came from this. And then let's distribute that 4, so we get a minus 16 plus 16 lambda, and then minus 4 plus 4 lambda. Now we look for terms that combine. I'm going to underline some of the terms that combine. Or you know what? Wait a second. We have a lambda cubed here. So let's just start with the highest power. Lambda cubed. Is there anything else lambda cubed? No. So, all right, we've got that. What else have we got? How many lambda squareds do we have? We've got 5 of them over here. Any more? Yeah, 7 of them over here. So the 5 plus the 7 means that we have 12 lambda squareds. And then how many just regular lambdas do we have? We've got minus 35 of them here, minus 6 of them here, plus 16 of them here, plus 4 of them here. If you add that all together, you wind up with minus 21 lambda. And then what else have we got? There's a 30 minus 16 minus 4. See that? 30 minus 16 minus 4, so plus 10. So this is a cubic polynomial. And even though I said this is a 3-step process, and I said step 1 is to find the characteristic polynomial. We just found the characteristic polynomial, but I think you know what step 2 is going to be. We're going to set this equal to 0 and solve. We're going to find solutions to the characteristic equation. I'm looking at this polynomial and I'm thinking, it's going to be hard to set this equal to 0 and solve, isn't it? What are we going to do if you set this equal to 0 and solve? This is hard to factor. And, you know, we're trying to do as much as we can in this class without calculators. So if we're trying to do this by hand, how are we going to set this equal to 0 and solve? So I'm going to show you an algebra trick that we could do instead. Instead of this form, we're going to get it into a different form. The steps that I did here kind of felt the most natural to me. You know, I was expanding, combining like terms, wound up with this in kind of a polynomial. It looks like it's in standard form. Let's go back 2 steps. And from here, let's try this instead. We're going to work with that step. And instead of expanding, let's factor this little quadratic, because this factors to lambda minus 1, lambda minus 6. And then look at this 4, and then this 4, and this 4. See, the 4, 4, 4 makes me think, let's make this 16, 1 minus lambda. And then what else have we got? We have a 2, 2, 2. So we could make this a plus 4 minus 1 plus lambda. Okay, so that's equivalent to that line that we had. Do you see why I did this? All three of these terms sort of have something in common. There's this lambda minus 1. Right here, this is a lambda minus 1. So this has a lambda minus 1. This has a lambda minus 1. This has a 1 minus lambda, but then there's a minus out front. So here's what we can do. We can say that this equals lambda minus 1, 5 minus lambda, lambda minus 6. Change the minus to a plus to flip the sign. And instead of 1 minus lambda, that becomes lambda minus 1. And then over here we have lambda minus 1 times 4. We did this algebra trick because now we see that every term has lambda minus 1 out front. In algebra, when we see that every term of a polynomial has something out front, it means that we can factor that out. So we can factor out lambda minus 1 times some big expression here. Well, it's not so big. It's not so bad. 5 minus lambda, lambda minus 6. What? Plus 16 and plus 4? That's where we're at so far. We're trying to get, just to be clear, what we're doing here is we found the characteristic polynomial, and we looked at it. We took one look, and we kind of got scared, and we said, all right, that actually looks scary to set that equal to 0 and solve, so let's try to get it into a different form instead. I mean, by the way, I think I can tell what one of the eigenvalues is already from this term, if we're going to set this equal to 0 pretty soon. So I think we know that lambda equals 1 is going to be an eigenvalue. But let's figure out what's going on in here. So this is lambda minus 1, and then I am going to expand this. So I got 5 lambda minus 30 minus lambda squared plus 6 lambda plus, combine the 16 and the 4 to get 20. Lambda minus 1 times minus lambda squared plus 11 lambda minus 10. Okay. So, I like this form better. I like this form better. You know what I don't like, though? When I'm trying to factor polynomials, if there's a negative out front in front of the squared term, I usually try to pull that negative out or flip the sign or something. Here's what I'm going to do. I'm going to pull the negative all the way out here. That way, what I have in here can be a positive. That's just kind of a personal preference. I do that sometimes. It means I'm going to have to flip the signs of this other stuff. So minus 11 lambda plus 10. You know, you could say that's optional, but I like doing that. Now, do you think this quadratic in here can be factored? It would be nice. Yeah, it does. It does factor. Factors to lambda minus 1, lambda minus 10. It's like the eigenvalues are just jumping right out at us right now. We can see what they are. So I'm about to move away the top page, but do you see how we had a characteristic polynomial that looked really hard? I mean, it's cubic, so it's not like the worst, but it still looked kind of hard to factor, or I should just say hard to solve if we set it equal to 0. But now look at this form that we got it into. This is so much nicer, and it's equivalent. But this is so much nicer when we try to set this equal to 0, and it is factored. All right, let's let's observe that lambda minus 1 is happening twice. So really, we could just write this as minus lambda minus 1 squared lambda minus 10. I told you this was going to be a long problem. I told you that this was a 3-step process. Well, that is the end of step 1. The good news is that step 2 is going to be very fast. All right, so just to be clear, this is the characteristic polynomial in a nice form. Step 2 is going to be find solutions to the characteristic equation. And as you can see, we've already done most of the work for that. So the characteristic equation is this. So it is minus lambda minus 1 squared, lambda minus 10 equals 0. From this, I get lambda equals 1, and from this, I get lambda equals 10. And these are our eigenvalues. So there are 2 of them. That's it for step 2. We're done with step 2, but we have more to do because this problem, if you remember how it was phrased, it said find the eigenvalues and bases for the corresponding eigenspaces. So this is part of the answer. We found the eigenvalues. I want to remind you of one thing before we move on to step 3. I just want to show you something. The characteristic polynomial that we found was cubic, right? Right here. So when I first saw it in this form, I saw cubic polynomial, I was thinking this might have up to 3 roots, right? A cubic polynomial has up to 3 real roots, and turned out that there's only 2. Okay. Step 3. Well, I said it's a 3-step process, and you know what part of the problem we haven't done yet. We haven't found the eigenvectors, the eigenspaces. So step 3 is going to be, for each eigenvalue, lambda, solve a minus lambda I times x equals 0, and write solutions x in parametric vector form. Use this to determine a basis for the eigenspace. So we're going to have 2 eigenspaces because we have 2 eigenvalues. So even though I said that this is a 3-step process and I said that this is step 3, we actually have to do this step twice because we have to do this step for each eigenvalue. So maybe you say it's step 3a and step 3b or whatever you want to say. Okay, so let's start doing this for, I think what I'm going to do, we could do this for lambda equals 1 or lambda equals 10. I'm going to start with lambda equals 10 because it doesn't matter which one we do first. And in my notes, I did lambda equals 10 first. So this is going to look like a minus 10 I x equals 0. This is just an equation we can solve. So finally, we get to do some like row reduction and some system solving. So this, as an augmented matrix, we have to go all the way back to the matrix A that was given. That was almost 2 pages ago. There's the matrix A, 542, 452, 222. Okay. So subtract 10i, so you're subtracting 10 from the diagonal entries. Negative 5, 4, 2, 4, negative 5, 2, 0, 2, 2, negative 8, 0. That's the augmented matrix of this system. And now we do row reduction. Let's see. In my notes, I did the row reduction. How many steps did it take me? It's a, 3x3 problem, so it took some steps. I think the first thing I did was I multiplied row 3 by 1/2. I thought that would make things a little bit simpler. Then I started adding multiples of rows to rows. I'm going to skip those row reduction steps. I think that you've seen enough row reduction from me, and you can do this for practice if you'd like. I did row reduction, and I got it all the way down to 1, 0, negative 2, 0, 0, 1. I mean, you need to be good at row reduction, so practice that if you'd like, on the steps that I left out. You should get this. And, I said that once you row reduce, you should write the solutions in parametric vector form. So we do have a free variable, right? X3 is free. So, what does row 1 tell us? Oh, you know what? Usually I would start with row 2, wouldn't I? I guess it doesn't matter. X1 minus 2x3 equals 0. So x1 equals 2x3. That's a basic variable written in terms of a free variable. What does row 2 tell us? It says x2 minus 2x3 equals 0. So x2 equals 2x3. So the solutions to this system in parametric vector form, well, x is x1, x2, x3, which we just found can be written as 2x3, 2x3, x3. So in parametric vector form, we would pull out the free variable x3, and then that's going to make this 2, 2, 1. Just to be clear, I'm going to say so. Two, 2, 1 is an eigenvector corresponding to the eigenvalue lambda equals 10. And so is any multiple of 2, 2, 1. I'm talking about scalar multiple. So a basis for the eigenspace corresponding to lambda equals 10 is set bracket this vector. Don't write span in front of it. It's a basis. A basis doesn't get span in front of it. There's one basis element. Okay, so the dimension of that space turned out to be 1. we still have a little more to do, right? We need to do this for the other eigenvalue. For lambda equals 1, we need to find a basis for this eigenspace. Solving the system, writing the solution in parametric vector form, and then writing the basis. I would like you to try this. I would like you to try this part. And pause the video and give this a try. All right, so hopefully you started with the system a minus 1I times x equals the 0 vector. And when I set this up as an augmented matrix, I have 4, 4, 2, 0, 4, 4, 2, 0, 2, 2, 1, 0. Okay? This row reduction is going to be simple enough that I'll just show the steps I did. I guess first I multiplied row 1 and row 2 by 1/2. Look at this. Have we seen a matrix like this before where like all 3 rows are the same? I don't know. Yeah, so I multiplied row 1 and row 2 by 1/2. I got this, and then I said, let's add multiples of row 1 to row 2 and 3. So I got 2, 2, 1, 0, and then the rest are all zeros. Okay, so that means that x3 is free and x2 is free. Let's see, what is row 1 telling us? We want to be able to write x1 in terms of x2 and x3. So it says 2x1 plus 2x2 plus x3 equals 0. So 2x1 equals negative 2x2 minus x3. So x1 equals negative x2 minus 1/2 x3. I mean, that's the basic variable written in terms of the free variables. So now let's try to write the solution set in parametric vector form. So solutions. So the vector x, which is x1, x2, x3, we just found that it can be written as negative x2 minus 1/2 x3, and then x2 and x3 are just themselves. So for parametric vector form, this time, because there are 2 free variables, we should pull out x2 times a vector, and x3 times a vector, because those were both free variables. And when we do this, I guess you get negative 1, 1, 0, and then over here you get negative 1/2, 0, 1. So you don't have to write this sentence, but I'm going to say, so negative 1, 1, 0, and negative 1/2, 0, 1. Does this mean that these are eigenvectors? I'm going to say these are eigenvectors. You don't have to write the sentence, but I want to be extra clear about this. They correspond to the eigenvalue lambda equals 1. And so is any linear combination. All right, any linear combination of the, you can see it, x2 times the vector plus x3 times the vector. That's a linear combination of those two. So anything that you get as a result is also going to be an eigenvector corresponding to lambda equals 1. So we can say a basis for the eigenspace corresponding to lambda equals 1 is set bracket these two vectors. And we did it. That's the end of the problem. It's probably the longest problem we've done so far this semester. Took multiple pages for me. And I didn't even show all the row reduction steps for that one part. Okay, so before we move on, I just want to quickly review something. All right. This was the problem as it was stated. We were given a 3x3 matrix. You could see that this whole process would be a lot simpler if it was a 2x2 matrix, right? But I wanted us to do a tough one. I wanted to do a long problem. So we found the eigenvalues and bases for the corresponding eigenspaces. It was a three-step process. Step 1, we found the characteristic polynomial. Step 2, we found solutions to the characteristic equation. And I put a box around it because that's part of the answer. You know, that's part of what the problem asked for. And then in step 3, we found the bases for each eigenspace. We had to do this for lambda equals 10. We had to do some row reduction. We had to figure out parametric vector form. And then we also did this for... We found it, and we put a box around it because that's an answer. And then we had to do it for lambda equals 1, and we also found that, and we put a box around it because that's an answer. That's part of what the problem was asking for. One thing that I would like to point out to you is if a problem says find a basis for each eigenspace, I would like you to make it clear, like we have two different eigenspaces. I'd like you to make it clear which basis goes with which eigenvector. I made it very clear that this basis goes with lambda equals 1. I also made it very clear that this basis goes with lambda equals 10. If you just told me, you know, the eigenspaces are this and that, I don't know which one goes with lambda equals 1 and which one goes with lambda equals 10. So in some way, you should make it clear. You could write a sentence like I did. Just make it clear. So there's a big problem. One of the eigenspaces had a basis with one element, so that dimension would be 1. And then this eigenspace had 2 elements, so the dimension would be 2. And I want to talk about that because I think that even though in the previous lesson we talked about eigenvectors and eigenspaces, I think this might be the first time that we've seen an eigenspace that's two-dimensional. So we have a topic we need to talk about, and this is called multiplicity. We found, here we can put a big dividing line here because we finished the problem. We found the characteristic polynomial, I'm abbreviating it, minus lambda minus 1 squared. That was it once it was factored, right? Do you notice that the linear factor that was squared, the linear factor that appeared twice, it wound up having a two-dimensional eigenspace. And the factor that was just appearing once wound up having an eigenspace of dimension 1. We say eigenvalue lambda equals 1 has multiplicity 2. And eigenvalue lambda equals 10 has multiplicity 1. I want to tell you that technically, I don't know if the book actually tells you this, but I want to tell you that technically this is called the algebraic multiplicity. And I'll tell you at this point, you know, there is another type of multiplicity, but we'll just call this multiplicity, we'll just call this the multiplicity of the eigenvalue because it's the only multiplicity that we need to discuss in this class. If you're curious, the other type of multiplicity that I'm kind of hinting at is called geometric multiplicity. The geometric multiplicity is the dimension of the eigenspace. And you might be saying to yourself, wait a second, isn't that the same thing? 2 and 1? The dimension of the eigenspace, those were 2 and 1. All right, let's talk about this. Lambda equals 1 had an eigenspace of dimension 2, which technically I'm saying that's the geometric multiplicity. Lambda equals 10 had an eigenspace of dimension 1. And you might be wondering, like, does this number and this number, are they always equal? So I guess we're kind of asking ourselves, is the algebraic multiplicity always equal to the geometric multiplicity? This is called an algebraic multiplicity because it's basically what we get from the polynomial. Polynomials are what algebra is all about. And then the geometric multiplicity is the dimension of the eigenspace. So to answer this in general, the multiplicity of lambda, and by multiplicity I mean, as we discussed above, it's what we get from the polynomial. This factor appeared twice. All right, it will be greater than or equal to the dimension of the eigenspace. So they don't technically have to be equal. In our example, they were equal. And they often are equal to each other. But it is possible that the dimension of the eigenspace can be less and the multiplicity could be greater. All right, so I have a problem that I'd like you to try. I know we spent most of this lesson doing this giant 3x3 problem. Part of the reason that it took a while was because I was trying to explain it in detail because it was the first time we had done all of this. I would like you to try a problem, but it's going to be 2x2. 2x2 is going to go much quicker. So I'm going to ask you the whole thing, though. So here's a 2x2 matrix. And this is an important kind of problem. I'm going to say find eigenvalues and bases for eigenspaces. So I'd like you to pause the video for a while and spend some time on this and then check back. So hopefully you saw that when it's a 2x2 problem, it doesn't take as long as the 3x3. Step 1, we find the characteristic polynomial. A minus lambda I, we want the determinant of that. So we want the determinant of this. Since it's only 2x2, this is minus 4 minus lambda, 5 minus lambda minus negative 6 times 3. Minus 20 plus 4 lambda minus 5 lambda plus lambda squared plus 18 from the 6 times 3. We've got a 4 and a 5 we can combine, a negative 20 and an 18. So altogether, I get lambda squared minus lambda minus 2. Okay, I think we'll be able to work with this. So that's the end of step 1. Step 2. Oh, by the way, you have to be extra careful in step 1, because if you find the wrong characteristic polynomial, it might throw off everything else about the problem. So maybe when you find the characteristic polynomial, double check your math, make sure everything looks good. The rest of it depends on this. So now we're going to find solutions to the characteristic equation. I'm abbreviating a lot here, but solutions to the characteristic equation, that's where we want A minus lambda I determinant to be 0. And you understand why we want the determinant to be 0, because that means that the homogeneous equation is going to have non-trivial solutions, which means we're going to find eigenvectors. So set it equal to 0. It factors. And I think we get 2 eigenvalues. So I found lambda equals 2 and lambda equals negative 1. And I'm just going to indicate that these are eigenvalues and put a circle around it or a box around it, because that's part of my answer to the problem. And it's the end of step 2. Step 3 is going to be the basis for each eigenspace. And you know, there could be some problems that sometimes might not even ask you to do all of this. You might get a problem that just says find the eigenvalues, and in that case you'd be done already. But if it asks you to go ahead and find the eigenspaces, then we do all of this. So we need to do it for each of them. So just pick one to start with. I'm going to start with lambda equals 2. And we need to solve the system a minus 2ix equals 0. Because any solutions, any x vectors that we find that solve this equation are going to be eigenvectors corresponding to lambda equals 2. The augmented matrix that I got was negative 6, 0, 3, 3, 0. So 1, 1, 0, 0, 0, 0. By the way, look, we got a free variable here. You might be wondering, do you think in these problems, do you think there's always going to be a free variable? Well, we're looking for non-trivial solutions. So yes, there will always be a free variable. because if there were no free variables, then we would have a unique solution, and the unique solution would have to be the trivial solution. So yes, there will always be a free variable in this type of problem. Let's see. Row 1 says x1 plus x2 equals 0. When I say there's always a free variable, I should say there's always at least one free variable. We saw in the previous problem there could be 2 free variables. All right, so solutions in parametric vector form. Negative x2 and x2, so x2 times this vector. I'll continue this on the next page, so I don't want to try to cram the solution into that corner. So the basis for eigenspace corresponding to lambda equals 2 is the set containing this vector. And you should have set brackets. Don't just write the vector. You need to write a set containing that vector. That's part of the answer. So we'll put a box around it. One more to go. One more. We need to do this for the other one. The other eigenvalue that we found. Oh, by the way, remember when we talk about bases, you know, this is one possible way to write a basis for this eigenspace. There are other ways. What if I said, instead of -1, 1, I could say -2, 2? That would also be a valid basis for this eigenspace. It would also be correct. But it's just more natural to just leave it the way it is. -1, 1. Let's just leave it that way. Why would I multiply it by a scalar? Just leave it, and it's nice and simple this way. Okay. Okay, so I need to do minus lambda I, but because lambda is already negative, I'm just going to write plus 1i. Minus a negative number, so I made it plus. So the augmented matrix of this system, -3, -6, 0, 3, 6, 0. I expect to see matrices that lead to free variables, so it's not a surprise to me to see this kind of structure, you know? It means that I'm going to have row 2 be all zeros and have a free variable. I guess x2 didn't have to be the free variable. x1 could be free, but we did have to have at least one free variable. Row 1 says x1 plus 2x2 equals 0. So x1 equals -2x2. So the solutions to this one you should have gotten that x equals x1, x2, which can be written as -2x2, x2. So x2 times the eigenvector -2, 1. That's going to tell me what a basis for the eigenspace is, but let's just make it extra clear and write it as a set basis for the eigenspace corresponding to lambda equals -1 is the set containing that vector. So 2 eigenvalues, 2 eigenspaces. There we go. So I think you should be ready to do these kinds of 2x2 problems, and the 3x3 problem that we did earlier. And I want to show you something. We're basically done with everything we needed to discuss in this section, but I have one more thing I want to talk about. One more extra thing. And it's actually in relation to the 3x3 problem that we did earlier. Earlier, we found and factored the characteristic polynomial of this 3x3 matrix, 5, 4, 2, 4, 5, 2, 2, 2, 2. And this took a while because it was tricky because we had to factor a cubic polynomial. And we basically did factor it just by doing some, clever algebra of grouping together terms and grouping together factors. But, if you have a 3x3 problem and a cubic polynomial, I want to show you an algebra trick that could help. And we could have done this earlier. But yeah, there's multiple ways to do algebra. So when we were trying to work with this determinant, 5 minus lambda, 4, 2, 4, 5 minus lambda, 2, 2, 2. So I'm going way back to the beginning of this problem when we were trying to find the characteristic polynomial. All right, I claim that this determinant is equal to the determinant that we get. You know what? Maybe I shouldn't do an arrow this way. I don't know. I'm erasing my arrow. It's not super important. I kind of feel like I should do this. All right, what I'm doing is I'm going to add negative row 2 to row 1. I wind up with 1 minus lambda. So I added negative 4 up here. Negative 1 plus lambda. Now that's a little tricky, but I added negative of this term to the 4 that was there already. And then negative 2 plus 2 is 0. Now this might look weird to you because did we just do a row reduction step, but I put an equal sign in between? Normally when we do row reduction, I tell you don't put an equal sign because normally when you do row reduction steps, you get two matrices that are row equivalent to each other, but that's not the same as two matrices that are equal to each other. So usually we don't put an equal sign. The reason I'm putting an equal sign here is because these are not just matrices, these are determinants. I'm saying that the determinant of this matrix equals the determinant of this matrix. And why is that true? Why am I able to do a row reduction step and still claim that the determinants are equal? It's because, remember, adding a multiple of a row to another does not change the determinant. So that's a cool trick, right? Because now I turned it into a 3x3 determinant that has a 0 in it. And this is going to be an easier determinant to find because whenever there's a 0 in a matrix, we can do cofactor expansion across any row or column, and we usually try to pick the one with the most zeros in it. So yeah, that's kind of a cool trick, isn't it? In fact, we could go further and do more row reduction steps. If we are adding a multiple of a row to another row, maybe we can get this to be even simpler. All right, so what I'm going to do next, I'm going to put an equal sign because I'm saying this determinant is equal to this. The step that I'm going to do here is I'm going to add -2 times row 3 to row 2. Let's try to get another 0 to show up. So row 1 is staying the same. And then this becomes 0, 1 minus lambda, minus 2 plus 2 lambda. And then this is still 2, 2, 2 minus lambda. I think the more zeros we get to show up, the easier this determinant is going to be. So you could just find the determinant from here now because it has some zeros in it, or you could look for other steps. I've got a clever trick here. Okay. I'm not going to add another multiple of a row to another row right now. There's a different thing that we can do that still does not change the determinant, and that is transpose. We could take the transpose of the matrix, and the determinant is still the same. And I'll show you why that's going to help us. Basically, what I'm trying to do right now is make step 1 a little bit easier in that big 3x3 problem that we did earlier. There's nothing that's going to make step 1 completely free. I mean, this is a 3x3 matrix that we're starting with, so it's going to take some work no matter what. But yeah, there was a fact that we said earlier in the textbook. It's in section 3.2. I think it was the lesson about properties of determinants. But one of the properties of determinants is that when you take transpose, it doesn't change. So we didn't change the determinant, so it's okay that I put an equal sign there. And now I can get back to adding a multiple of a row to another row. I'm going to add row 1 to row 2, which doesn't change the determinant. So I get 1 minus lambda, 0, 2. Now, normally you think about row reduction, you would never really think to do transpose in the middle of row reduction. But we're doing this with a different purpose in mind. We're just trying to make the determinant easier to work with. It's not like I'm solving a system right now. So technically, I'm not doing Gaussian elimination. I'm just working with determinants. Look at that. We have a 0 and a 0 here. Now I think the determinant would be easier to find because we have a bunch of zeros. I would probably do cofactor expansion across the first column, top to bottom. But guess what? I'm not going to do that yet because I see this 1 minus lambda and this minus 2 plus 2 lambda, they kind of look similar to each other to me. They kind of look like I want to add 2r2 to r3. Isn't that going to get us another 0? So row 1 stays the same. Row 2 stays the same. Row 3, we get a 0 here. And this becomes 10 minus lambda. This is now the determinant of a triangular matrix. Remember we had a fact about determinants of triangular matrices? It was a fact or a theorem, and it basically said, take the diagonal entries and multiply them. So this determinant must equal 1 minus lambda, 1 minus lambda, 10 minus lambda. And that is what we found earlier. That is what we found earlier, except when we found it earlier, we wrote it a little differently. We had a negative out front, and it was lambda minus 1 squared. And then it was lambda minus 10. So, same thing we found earlier. So which method was easier? I'm not redoing the entire problem. I was basically redoing step 1 of that problem in a totally different way. So if you want to, you might be able to use properties like this to make it easier to find the characteristic polynomial. You can actually always get a square matrix into triangular form because triangular form is row echelon form. But the tricky thing is make sure that you're doing steps that don't change the determinant. You know, I'm adding multiple of a row to another row. I'm doing transpose. Yeah, so we had some tricky algebra when we did the problem earlier dealing with a cubic polynomial. This is also a little bit tricky. And you know what? You don't have to do every step that I did. You could actually just do like the first 1 or 2 of these steps. You could even just do this first 1 step, and now there's a 0 in here, and say, oh, I could find the determinant a little bit easier now because of that 0. Or maybe do like half of these steps. Maybe do like the first 2. You have a 0 and a 0. That's going to help. Do as many steps like this as you like. It's optional. It's just, you know, would you rather work with the algebra the way we did earlier? Or would you rather work with it in this sense? Either way, you get to the same characteristic polynomial. So I just thought that was a cool thing to show you. If the problem is 2 by 2, then I probably wouldn't even bother with this kind of stuff. 2 by 2 determinants are pretty easy. But for a 3 by 3 problem, I thought this was worth showing. Or maybe if you're lucky, you'll get a 3 by 3 problem that already has some zeros in it. You know, if it already has some zeros, then maybe the problem won't take as long anyway. All right, so we're going to wrap things up here. All right, so that was our lesson on the characteristic equation. We only did a couple of problems because they take a long time, but I hope that you see that like a 2 by 2 problem doesn't really take as long. 3 by 3 problem, whether it takes long or not, depends on the matrix. You know, if there's a bunch of zeros in it or the algebra works out nicely, it'll be quicker. The one that we did actually took a while. So the next lesson that we have is going to be on a topic called diagonalization. And diagonalization is going to use the skills that we just covered today. So we're going to need to know how to find the basis for each eigenspace before we can do the next lesson. And in that next lesson, you might see another 2 by 2 example of this. But we're going to go further with it, and we're going to say, what can we use eigenspaces for? The answer is diagonalization. That's an application of this, and it's something that turns out that it has some practical uses. So stay tuned for that. That's it for now, and I'll see you next time.